All right. So now for something a little different. Like was introduced, my name is Patrick Smith. It's my colleague Brian Rodrigue. We're from Excella. We do full stack custom software development, everything from data, DevOps, Agile, and everything in between. We're located right here in Arlington. Specifically, I'm one of the data science leads, and Brian is one of the data engineering leads. We're going to talk about how we can integrate artificial intelligence applications with Graph, specifically Neo4j, and some of the ideas and methods we can work to do that. So just a little introduction here, like I mentioned. Excella, we do both commercial, we do federal, we do a little bit of everything. We've been around since the early 2000s. Very proud of kind of our expertise across the full stack areas. And then our data team, we are made up of data visualization, data engineering, and data science. We're a fast-growing group within Excella, fairly research-focused. We do a lot of kind of just pro bono, if you will, kind of open source research and development efforts, which we'll talk about a little bit. So what are we going to talk about today exactly? The case of artificial intelligence and Graph is actually kind of interesting. Just want to start off here. Raise your hand if your company is using AI applications actively in production right now. Okay. Of those who raised their hand, who's working on those directly? Okay. So we're going to talk about a few cases where we have these in-production systems for artificial intelligence applications with Graph. One is a customer service case, and one is a fraud detection case. And I kind of want to cover three areas here. First is how do we intelligently ingest and retrieve data specifically from unstructured sources and put that into our Neo4j graph. How do we reason on top of that graph with something called graph embeddings and artificial neural networks? And then how do we actually reason and grow our knowledge within our graph? So those three topics I kind of want to touch on throughout the course of the presentation. So a lot of what I'll talk about today came out of a project that we started kind of as an internal research development project called Mako. And this is based on really trying to deliver value in active research within the artificial intelligence community as solutions. So let's look at some of the most pressing problems out there and how to deliver AI-based solutions to it with novel research that we've created, as well as some of the most cutting-edge techniques that we can find. And it's really all math-based, right? We consider ourselves primarily mathematicians above anything else. It's really interesting, especially when you look in this field. When you combine something like AI and Graph, you're really combining two things that have their roots in some of the earliest research in computer science and mathematics, and we're really bringing that to the forefront in ways that we could never really think of before. Just a little bit of our experience in working with this. This kind of talk came out of something we developed called Dale. Dale is the Deep Answer Learning Engine. It is a custom intelligent agent that we developed. And Dale is interesting. So it was designed to respond to tier 1 customer service requests. We developed our own artificial neural network structure for Dale, and it's basically designed to understand context. And so if you think of a situation like you are a client of a hospital or a doctor, and you are sending in a message and you want to know about a very specific circumstance in a very specific situation. So say you had a surgery, an operation, or need medicine or something. There's a lot of context and nuance and past information and documents that have to do with what you are talking about. And so one of the things that we wanted to accomplish with Dale is how to understand that nuance. And so how do I understand the context of the sentence? What exactly are you looking for? What exactly are you talking about? How can we retrieve those documents, and how can we actually synthesize it in a generative way where we are making the most human and accurate-like response? So we put out a few papers recently. One is on the mathematical structure of neural networks. We did a lot of research around basically embeddings, which I'll get into, and something called Lie groups, which is a way we can represent things in mathematical space. And from that came an algorithm we developed called Liger. Now, if any of you have worked with data scientists or are data scientists, you know that there are algorithms out there called GLOVE and Word2Vec, which are pretty common for for turning words into math. And we basically expanded upon that and made a more generalized version that can take into greater context and has a better accuracy. And we also developed something called the geodesic neural network, which is a new form of neural network. Again, not the focus of this talk, but happy to talk with anybody afterwards about that. So aiding AI with graph, what exactly can we do here? Just breaking this down into a few sections, kind of the traditional ways you can look at this is looking at your nodes. So retrieval, recommendations, clustering, classification, link prediction, things of that. Those are all things that we'll talk about, but you can move beyond that. And one of the things that I want to focus on is how we use graph as a rich data store, retrieve the latent information from that graph, and then reason beyond that. So with that, I'm going to turn it over to Brian, who's going to talk a little bit about our problem statement, our backend, and the engineering side of things.
So as Patrick mentioned, and we were working on trying to create an intelligent agent that's able to reason through and help out with Tier 1 service requests. So the actual case that we're looking at is for a federal client. They have, I'm not sure if you guys have ever seen this before, a series of very complicated forms. There's a lot of eligibility and nuances between them. To be honest with you, it wouldn't matter whether it was the SBA or the insurance forms that you were filling out, any other grants that you were applying for, immigration, pretty much most of the places within the federal space, they're going to have a lot of complicated forms. And whenever people that were from the outside were taking a look at it, what they found was that it was very confusing for them to work with. It was very costly if they made a mistake. In some cases, it was costly in terms of money, and it could also cost them years in order to try to recover from that. And so there was a lot of uncertainty that came from that, which meant that those people had a lot of questions, and they ended up hitting up the Tier 1, the service desk at the agency on a regular basis. So the business case for us was to find a way to help reduce those calls and to be able to maybe route and answer some of those questions before they hit the Tier 1 desk. So our technical response for that was going through and saying, okay, with AI, what we can do is we can use the deep learning in order to view the questions that they've gone through in the past. We can look at the groupings and be able to see the responses that we typically have for that. And then we can also use the graph in order to provide context. If someone was asking a question about their status on a particular form, they might be looking not just on that particular form, but the question that they were asking might have implications on other forms upstream or downstream. And so part of this was to be able to provide context. So we're using the graph in order to provide context on the overall system at the particular agency. Embedded in there is not only the details for the forms, but also going through and including things like processing times, eligibility requirements, as well as costs, because all of those things come into play whenever people are looking at the forms. What we found as we were going through and building it out was the agency was so excited to see all of their processes documented in graph format. They also realized that whenever you go through and look at the public-facing website, what they found was a series of links that show that you could find a link to the actual form so that you could print it off and fill it out, which was awesome. They had the actual language from the legal requirements for eligibility on the forms. And it was all it was the step-by-step version of things. What wasn't really provided was that end-to-end view of how to go through and navigate the agencies and the processes. And so, doing okay still? So while we initially were going to just provide context to the AI, actually we skipped one. What we were initially just going to provide context to the AI, what we found was they were so excited about the idea of being able to see their graph that they wanted a separate front end to be able to go through it quicker. So they're now building a front end that will hit their graph directly. We've embedded the questions and the answers for the eligibility to be able to help people walk through the process. Ironically, you won't actually see it because the Neo4j stuff all sits on the backside, but it would replace a lot of the systems that they were using that were manually built and have to be maintained separately. So the tech stack that we were using for the initial build out was trying to extract information from end users. So we used a lot of the low CSV information. The front end that we're building is a React front end that pulls the information directly out of the database in terms of questions, answers, and taking them through the process. For the interaction with the AI, we're using Pi to Neo. And of course, everything that we're doing is being built in the cloud. So it's an AWS implementation with a complete CI pipeline. And as we transition the rest of it out of the build-out phase and into maintenance phases, we're removing the load CSVs and replacing it with a custom front end and having automated uploads that scrapes data not only from the internal systems to be able to update any cost or any processing times, but also because there are links to other agencies for parts of the process, there's scraping that goes through and pulling the data in from those other spots.
All right, so let's talk a little bit about this kind of AI structure. And just for clarification, usually when I talk about artificial intelligence, we're talking about deep learning, which is deep neural networks. So artificial neural networks that are several layers deep. We can, actually, let's go here first. This is basically our core inference engine. So if a question comes in, so like I said, that complicated question that's coming in, we first embed that question. And I'll talk about embeddings in a bit, but it's a way that we can translate words into math. That gets embedded, and so now we have a representation of that question, and we send that to two parallel networks. And so these are pretty standard networks. We use a convolutional neural network and a recurrent neural network at the same time. Recurrent neural network is really good at looking at sequences. So for sequence modeling, words that are similar to each other, words that are next to each other, and the convolutional neural network, which typically you'll see actually for computer vision tasks, is really great about looking at context overall. So we're basically looking at two different segments of the document, and so we can get two different representations and get a better understanding of what's being said as a whole. Those get put into something called a fully connected layer, which is basically a multi-layer perceptron, and that goes through a generator. So if any of you are familiar with Ian Goodfellow's generative adversarial networks, we're basically using the generator aspect of that and going to an answer. Where Neo4j comes into this is we have a question, and once we get to that fully connected layer, often, as Brian said, there are tertiary documents and forms that have to do with that question that we need to pull back. And we could train on those, but then it wouldn't be the exact way as if we need to, say, attach a document or bring back a specific piece of information or perhaps bring back somebody's individual processing time. And we could do that programmatically, but when you get a graph that gets increasingly big, where you just have data that gets increasingly big, we wanted to find a way to do essentially intelligent search so we could speed up that process and return the more accurate information that was relevant to that person as quickly as possible. And so that's where this kind of process comes in. So what we're talking about a database. Here's just a small snapshot. We have things of processes in general, and this is a highly simplified version, but processes, forms that folks have to fill out, individual documentation. In here would be properties on those nodes, and other information relating to process. And this would get built out larger, and so this is looking at an individual process, but we might have one that has to do with policies, policy documents, laws, things of that nature, what pertains. And so essentially what we're trying to do here is parse down the amount that a customer service agent would have to actually look through relevant policy documents to search, to send an email back. Instead of having to look through 50 pages of documentation, instead we can find the exact part of the documentation that's relevant to them and send that back. So like I said, a lot of this works on something called embeddings. And embeddings are essentially a way that we can represent most things in the world, usually unstructured information, in math. And so frequently you'll see this in the term of word embeddings. And so essentially what we're doing in mathematical terms is we're taking language and we're embedding it in low dimensional space on something called a manifold. The kind of layman's explanation is we are capturing a lot of the latent information, which is in unstructured data, and we're putting it in a mathematical space. And what that allows us to do in the artificial intelligence community is do all types of computation over it. We can usually overlay most types of artificial neural networks on top of an embedding structure and get a lot of latent information out of there. And so that is exactly what we're doing with graph. And this is something called graph embeddings. So we're taking this beyond natural language, and we are physically embedding the graph. Graph embeddings come in a few different ways. We can embed the entire graph. We can embed the edges in the graph. We can embed the nodes. We can embed any individual part of the graph. Each have a certain kind of cost and benefits to doing that. But what we're doing is we're extracting the information from the graph so that we can do kind of higher order computations on them. Like I said, we're just converting to vector space there. Going to skip ahead a little bit. So what are some of the things that you can do with this? And these are actually citing past research. We can do node labeling, regression, edge prediction. One of the a paper came out about a year ago that proved that you could predict missing information in social networks. So what is a user's age or what is their location based on these computation after graph embeddings. Categorization, or even some functions in the medical community. Let's skip over that. So just a little bit more on these embeddings, because really this is the structure and this is the core of how we do artificial intelligence on top of graph. And so if any of you have heard of these structures before, I think it was 2010, a paper came out called Deep Walk. And Deep Walk was the first kind of example of how we can apply embedding structures to graph. And now we're using kind of more advanced sequence sampling methods. And it's getting more advanced, and it's a very active area of research right now of how we can represent graphs in a mathematical space. So how does this work, right? We have nodes, we have connections, and we have groups. Basically what we're doing is we're transforming this into matrices. So a lot of what we do in deep learning in the artificial intelligence community is nothing more than mathematics. It's frankly a lot of linear algebra, vectors, matrices, things of that nature. And we are bringing that forward. We're doing an embedding structure, and we are doing analysis on top of that. If any of you are familiar with the data science terms, this is very akin to dimensionality reduction, so principal component analysis or TISNE or something of that nature. We're basically visualizing data in a mathematical space. So for our particular use case here, we use something called GemSEC. GemSEC actually came out 4 months ago. And it's really interesting because it works on top of a lot of the research that was done on graph embeddings previously. And it learns clusters and embeddings at the same time. So clusters we can think of, right, as grouping, like natural groupings of what is in our database. And so this becomes really useful for applications like fraud detection or any other community detection where we have a lot of information of, say, fraudulent and non-fraudulent data in our database. Hopefully with a rich enough data set, which is provided by the graph, we can start to detect fraudulent communities while learning our embeddings. Following up on that, from a mathematical standpoint, we basically embed a clustering cost into the full embedding cost function and minimize that at the same time. Where we go from there is we have our graph, we turn the graph into mathematics, and then we send that math to something called it's a class of models called variational inference answer selection. Specifically, it was something that came out several years back called the neural answer selection model, which is really designed for question answering tasks, really like an IBM Watson trying to figure out how to answer Jeopardy questions. But we found this is really applicable with GemSEC to actually figuring out that relevant information in a customer service circumstance. And so the way that this works is we return from our embeddings our clusters, so our neighborhood that might be relevant to the information that we are seeking and the actual information in mathematics. What we do is we run this model on top of that, which will actually look through those individual potential tidbits of information which might be relevant to answering our question, and we will select which ones, just like a question answering sequence, are relevant to that particular question that a customer asked. It's just a little bit, basically a query gets sent in, and this is just a tidbit of what I was showing earlier. A query gets sent in, that gets vectorized, so basically that gets turned into math via our Liger algorithm, That query is sent, and we find the relevant information in Neo. That runs back and gets embedded, so we get our cluster. We get that in an embedding space, and then we reason over that embedding space with the answer selection model to determine the information that is correct. And then this gets put back into, if you remember what I was talking about earlier, this gets put back into our grader model. So not only do we have the context and the information that's coming from the two network structures, but we are returning the documents, various other structured information relevant to providing an answer. How are we doing on time? I think we're running low on time, but I just want to briefly touch on another system that we worked with, and this is utilizing artificial intelligence and Neo4j for essentially fraud detection applications. And so, or looking at documents and determining fraudulent circumstances. So this particular scenario was done in the case of an OIG, and essentially they had audits and grants and things of that nature, and they wanted to determine which individual grant structures should be investigated at any given time. And we have essentially past audits, both fraudulent and non-fraudulent, and additional grants data. The goal here was to try to build a holistic look at a grants process and determine which of those, what was fraudulent in that process. And what we did essentially here was combine, again, our embedding operations with our latent graph information and some intelligent retrieval methods. So just quickly walking through this, because I know we're short on time. A lot of this is not new. What we do is we extract the information that we have. So frequently it's in PDF form. We have audits and things of that nature. We use a simple Python package for PDF mining and an OCR technique using Tesseract, which has been around since the 80s, I think, but is still in frequent use for actually recognizing the structured information in there. So that's tables and figures and things of that nature. And so we return our information from there. We also take in tips and call center information, and we are using the Google Cloud speech-to-text API, which is, in my opinion, one of the more accurate ones out there. And then what we do is we combine that in a memory file and or in memory in Python, and we do entity recognition over that. And so this is where we start to actually pull out the first round of what is important within those audit documents, or that situational, a full picture of the situation, so we can start to build a graph. And we also add in another neural variational inference. So this is, we basically put in topics and other relevant information that we can glean from the document into that situation. And what we end up with is a very ugly looking graph. And this is a super simplistic model of basic entities. And so this isn't very useful to us. And so we essentially need to reason, and we need to edit over this. And so what we do is we start to retrieve information and update those node properties and connection properties and add information to the graph to actually make this a useful graph. And we do that by two ways. So we iterate over our nodes, and we basically do an automated web search to find additional information. So this is targeting things like grants.gov and other structured information databases to try to retrieve that information, public information websites, and some other sources that we've identified to basically glean information on actors who were involved. So, in a particular fraudulent situation, maybe a similar accountant or someone like that was involved in several situations. And we return that to enrich our graph. And then on top of that, we can do reasoning and additional operations. Now, Neo, I know this past year actually released on-graph operations, so some of the more common on-graph operations like PageRank, pathfinding, and label propagation for group recognition. Those are super useful for actually updating the information within your graph. But I want to kind of focus on talking about the deep side of this. And what we do is we look at this again from the embedding structure. Brian, I don't know if you want to kind of jump in and... I'll
let you go with it for now.
All right.
I'll jump in if you're off.
All right. we kind of look at again, look at these relationships through an embedding structure. And same thing with the GemSEC embeddings. So we pull the nodes in, and we do some computation over that, so that will give us our actual, again, clusters. Label propagation can also give you your clusters, but we found that deep methods work better, and this particular method, GemSEC, shows a 9% improvement over the state-of-the-art clustering methods for graphs. So this allows us to start getting our general groupings of fraud, and we start to build from there. And this is all run on GPU-enabled TensorFlow in the cloud. So like I keep going back to reasoning. Ultimately, what we want to talk about here is, is what we're looking at is a given situation fraud or noncompliance. And what we've ended up at this point, you can think about it, is we have a graph that has rich information on fraud and not fraud within a certain agency's grants structure, and this goes back many, many years. We've gleaned in public data, we've gleaned in several other data sources, and so we have an extremely rich data source within the graph. That provides us with an extremely rich embedding structure. And so when we actually look at how to do computations over this, we can look at all of the latent information that we can possibly glean from the world on the same embedding space, if you will. It's called a manifold. And so what we do from there is pretty standard deep learning work where we run a classifier, specifically a recurrent neural network, over that for fraud predictions. And then we've actually started to look into, for actually iterating over the connections in the graph, something called the recursive neural tensor network, which was released in 2013 for knowledge base completion. And that has allowed us to create new connections and basically complete our knowledge base of a fraudulent situation with artificial intelligence. Just a couple other things I want to just touch on quickly. There is something really neat that has come out called graph convolutional neural networks, and this actually puts this whole structure that I've talked about in a single model where you can do kind of that embedding and extraction process at the same time. And that should be promising if you want to stay to a particular graph. It's really good for specific scenarios. I just want to kind of close out here. Like I said, I know I've kind of rushed through this and there's a lot of dense topics, so I apologize, but there is a limited amount of time. I would say the takeaway here is graph embeddings. We can do a lot of computation and glean a lot of information beyond what we're able to find just by simple, not simple, but like in-graph structures and just simply looking at the graph by actually taking it out, but still utilizing the graph structure and using that in an embedding format. And we can, I would say, looking forward, something we're investigating and something I think the community could potentially investigate is how to more closely integrate some of these deep methods with the graph, from a computational standpoint, so we don't have to do so many transformations, and just improving the pipeline overall. If you're interested in our research, we've published several research papers on kind of embedding structures and deep learning recently. You can find them on archive. So thank you for putting up with my talk of deep learning, and hopefully you learned something.